Okay, let's continue the topic of logic. Well, I want to start with solving a question. Well, it tells you, you know, write each statement in symbolic form, like, P, Q, R, and says when you assign letters to simplest statements, make sure that they're not negated. For example, instead of it's not cold and you called it P, P is it is cold, and then ask you to make a truth table, and then use the truth table to indicate one set of conditions that makes the compounded statement false, or state that no such condition exists if it doesn't exist. Sure. um, the question says, well, that's from your textbook. If you do your homework right after class, then you will not fall behind. And if you do not do homework right after class, then you will. Okay? So, you do your homework right after class. I can call that P, and you fall behind. We can call that Q. Okay? So, P, you do homework right after class, and Q, you fall behind. So it says not negated, so I do not choose you will not fall behind. I choose you fall behind. Okay, behind. Okay, that's part A. Then it says make a truth table. Okay, let's change the statement into symbols. If you do your homework, if you do your homework right after the class, then okay, you will not fall behind, not Q. So we have a comma. Whatever you have before is one group, whatever you have after is another group. And, okay, after we have another group. If you do not do your homework, if not P, right after class, then you will fall behind. Okay, so here's the statement that we have. So we can make a truth table for that, and then it says find a set of condition that actually makes the statement false. Okay, so let's see, can I draw a truth table right here? Okay, let's see, that's PQ. Okay, I'm gonna make a truth table right here. Okay, we have PQ. Let's start with P and Q. We have two statements, so we have four possibilities. For half of them, P is true. For half of them, P is false. When P is true, Q is either true or false. And when P is false, Q is either true or false. Here we go. If P, then not Q. Okay, so we need not Q, and then the other one is if not P, then Q. We need not P too, okay? So what I'm gonna do, I'm gonna make not P and not Q first, which is really easy. Not P, well, it's the negation of P. Whatever you have for P, not P has the opposite logical value. So it's false, false, true, true. Whatever we have for P, I made that the opposite. And not Q is the opposite of Q. So true becomes false, false becomes true, true becomes false, and false becomes true. Here we go. So first I make if P then not Q. If P then not Q. Guys, be careful. P, the first column, is your antecedent, the start, not Q. Okay, the fourth column is your consequent. Okay, your start, look at the first row. Your start is true, consequent is false. So conditional is false. Look at the second row. Your start is true, consequent is true. So conditional is true. Look at the third and fourth row. Your start, your antecedent is false. You don't even need to look at your consequence. So conditional statement is considered true. Here we go. Now I'm gonna make the other one. If not P, then Q. If not P, then Q. Okay, be careful. Not P is the third column, okay? That's your antecedent, that's your start. And Q, the second column, is your consequent. Okay, so your start, look at the first row for not P. Okay, look at the first two rows. Okay, your start is false, conditional statement is considered true. Okay, now look at the third row. Okay, not P is true, that's your start. Consequent, Q is true, so conditional is true. Look at the fourth row. Your start is true, right? Not P. And your consequent is false, so here it is, false. Now what we have, if P, then not Q, and if not P, then Q. So we have and between these two columns, right? Between column 5 and 6. Okay, for and both must be true to have a true actually statement, right? Okay, so look at the first row. If P then not Q is false. If not P then Q is true. So for and conjunction both must be true. One is false, you get false. Look at the second row, both are true. Very good. For and both must be true to get the true value. Look at the third one. If P then not Q is true. If not P then Q is also true. Both are true, you get a true value. Look at the last one. We said that both must be true. One is false, you get a false value. Okay. The question, part C, was asking you to find one set of conditions that makes the compound statement false. Okay, guys, here's your compound statement. Compound statement. You made it, right? So when is it false? That's the first row and last one. Okay? So it's just one set of conditions. So just choose one of them. For example, I choose the first one. When is it false? When P is true and Q is true. Okay, so I say that set 1. Okay, when P is true and Q is true. In that case, the compound statement is false. Well, if you want to actually introduce another set, I call that set 2, but it just wants you to give one set, okay? So choose any of them that you want, okay? So choose either set 1 or set 2. So set 2, okay, that's when compound statement is false. Look at P and Q. Well, P is false and Q is false. So when P is false and Q is false, the compound statement is false. So this is how we answer this kind of questions, okay? So what I did, I drew a truth table for the compound statement, and I just picked one set that makes the compound statement false. That's when P is true and Q is true. Okay? So, well, De Morgan's law, well, that's really, really interesting. Well, let's say you have conjunction or disjunction, okay, between two statements, and then you want to make the whole statement negated, okay? For example, you have P and Q, and you want to negate the whole statement. Okay, so what happens? Guys, this sign is like equal, okay? Here you go, doesn't matter, okay? So negation acts on P, okay? Well, changes that to not P, makes sense. Negation acts on and, changes that to or. So that's De Morgan's law. The negation of and is or, the negation of or is and, okay? Well, negation acts on Q, and then you have not Q. So the negation of P and Q is not P or not Q. Very, very similar. Let's say you have P or Q, and you want to negate the whole thing. Again, negation acts on P, changes that to not P. Negation acts on or, well, changes that to and, De Morgan's law. Negation acts on Q, now you have not Q. So the negation of P or Q is not P and not Q. Very, very easy, right? Okay. So, okay, variations of the conditional statement. Well, let's say we have a conditional statement, if P then Q. Okay, guys, that's the conditional, right? First one. Look at the second one, converse. If I just change the place of P and Q and write down if Q then P, we have the converse. Be careful. If you change the place of P and Q, right? And then you have the converse is not equal to your conditional statement. So conditional statement and its converse, they're not equivalent. Okay? Well, when I change the place of P and Q, if I negate P and I negate Q, it's like, okay, so let's say, yeah, let's just start from the condition. Sorry, we have if P then Q, okay? If I just negate P, look at the third one, not P, and then negate Q, just write not Q, okay? And write down the conditional, if not P then not Q. In that case, we have inverse, okay? Be careful again, inverse and conditional, they are not equivalent, okay? Now, if I change the place of P and Q and then negate them, like I have if P then Q, then I write down if not Q then not P. I have contrapositive. That's really, really important, guys. Conditional and contrapositive, they are equivalent. So if P then Q and if not Q then not P are equivalent. Well, to test, you can draw a truth table for each one separately. You will see that the final columns are exactly identical, okay? So here we go. So if you have a conditional statement, well, converse is when you change the place of P and Q. So conditional is if P then Q, converse is if Q then P, and inverse is like, when you have if P then Q, you just negate P and Q. So you have if not P then not Q, okay? Be careful, conditional and converse are not equivalent. Conditional and inverse, they're not equivalent. Well, if you have a conditional if P then Q, and you change the place of P and Q, okay, and you negate them, well, you make if not Q then P, if not Q then not P. In that case, you have contrapositive, okay? A conditional and a contrapositive statement, okay? They're equivalent, okay? So if P then Q, that's your conditional. If not Q, then not P is your contrapositive. That's very, very important. We will come back to this topic, through the semester, okay? So, well, I'm gonna use this to talk about some forms of reasoning. Well, we argued that if you're given a statement, okay, if you are given an argument and you want to see whether or not the argument is logically valid, well, you follow 4 steps. You choose P, Q, R, like that. You change the whole argument into symbols. You draw a truth table and then you make sense of your truth table to see whether or not the argument is valid, right? Well, sometimes when we look at the structure of an argument right away, just by looking at the structure, we can find out whether or not the argument is valid, okay? So here I'm gonna just talk about some structures. Just when you look at them, you can find out whether or not they're valid, okay? So one is directly, direct reasoning. You have if P then Q, then you have P, therefore you have Q. So if P then Q, well, P, they are your premises, okay? And then Q is your conclusion. Any argument that has this form is logically valid. We call that direct reasoning. So if P then Q, let's say P is Eric passes Janet 1101 exam, okay? So Eric passes Janet 1101 exam, and Q is he will finish his program. Okay, I'll give you some time to think about it, okay? So P, Q, P, Eric passes Janet 1101 exam. Q, he will finish his program. Okay, now we have if P then Q. If Eric passes the Janet 1101 exam, then he will finish his program. If P, then Q. Eric passed the Janet 11-1 exam, P. Therefore, now you have your conclusion, Q. He will finish his program. All the arguments that they have the direct reasoning structure are logically valid, okay? So, now look at here, the fallacy of converse, okay? So, we said that if we have a conditional, if P, then Q, right? So, converse is if Q, then P, and conditional and converse, they're not equivalent, right? So that makes sense. If you have an argument that has the structure of converse, you have if P then Q, and then you have Q, therefore P. In that case, the argument is not logically valid, okay? These are your premises. Here is your conclusion. Any argument that has this form is invalid. Well, let's say P is I have the flu, and Q represents I have a sore throat. Okay. I tell you, if I have the flu, if P, then I have a sore throat, Q. I have a sore throat, Q. Therefore, I have the flu. No. This is a fallacy of converse, and this argument is invalid. Okay, look at here. The fallacy of inverse. We say that if we have a conditional, if P, then Q. If you negate P and Q and write down if not P, then not Q, you have the inverse, and conditional and inverse are not equivalent, okay? So, if you have an argument that has this form, you have if P, then Q. Then you have not P, therefore not Q. Well, it's the fallacy of inverse, and the argument is invalid. So these are your premises. Here is your conclusion. Okay. Let's say P is you study, and Q is you will pass the exam. The exam. Here we go. Well, if you study, if P, then you will pass the exam. Q, you do not study, not P. Therefore, not Q, you don't pass the exam. Okay? Well, so any argument that has this form is logically invalid. Okay? A conditional statement is not equivalent to its inverse. Contrapositive reasoning, guys, this is very, very important. We will go back to this kind of reasoning when we are talking about scientific method, and towards the end of the semester when we are talking about evaluating information. We will get back to this. This is very, very important, okay? Contrapositive reasoning. Well, we said that if we have a conditional statement, if P then Q, right, it's equivalent to its contrapositive, which is if not Q, then not P. So I have if P then Q, then I have not Q. These are the premises. Therefore, the conclusion is not P. Conclusion. Any argument that has this form is logically valid. Well, let's say P represents the cat touches the feeder, and Q represents it wants to be fed. The cat wants to be fed. Here we go. So, if the cat touches the feeder, if P, then it wants to be fed, Q. The cat doesn't want to be fed, not Q. Therefore, not P. The cat doesn't touch the feeder, okay? So, any argument that has this form is logically valid, okay? if you have if P then Q, it's equivalent to if not Q then not P. It's contrapositive, right? Okay. Another form of reasoning which is valid is the transitive reasoning. You have if P then Q, then you have if Q then R, then from the first antecedent you go to the last consequent. Therefore, if P then R. Okay? For example, let's say P represents John gets a raise, and Q represents John buys a house, and R represents he will run for a position on the neighborhood council. So John runs for a position on the neighborhood council. Here we go. Well, look at the first line. If P then Q. If John gets a raise, then he will buy a house. Look at the second line. If Q then R. If John buys a house, then he will run for a position on the neighborhood council. Therefore, now that's your conclusion. If P then R. If John gets a raise, then he will run for a position on the neighborhood council. So this is the transitive reasoning. Any kind of argument, right? Any argument that has this kind of structure, transitive reasoning, is logically valid. Okay, it's a valid argument. Okay, so well, there are two terms that it's important to get familiar with. One is self-contradiction. Okay, let's say you have a statement. Okay, you draw a truth table for your statement, and actually all the values that you see is false, so we call that self-contradiction. One example is P and not P. You have P, it's either true or false. You write down the negation, the opposite value. When it's true, negation is false. When it's false, negation is true. And then you make P and not P. For and, both statements must be true to have a true value. You see all the values are false, so we call that self-contradiction. Okay, so what is tautology? Well, if you have a compounded statement and you draw a truth table for that, and all the values that you get turn out to be true, then you have tautology. Okay, so tautology. When we wanted to find out whether or not an argument is valid, right, we were following 4 steps. Using P, Q, R like that, changing, step 2, changing the whole argument into symbols. Step 3, making a truth table, and step 4, make sense of the truth table. For step 4, guys, we had 2 ways. We could make premise 1 and premise 2, and then one column for if premise 1 and premise 2, then conclusion. If all the values were true, you had a valid argument. We call that a tautology. Another way was that when you make your premises and conclusion, you can stop. You just focus on premises and conclusion. You go row by row. If you find any row for which all premises are true and conclusion is false, then you have an invalid argument. If you cannot find such a row, you have a valid argument. Okay, so this is the meaning of tautology. Well, you have a statement, right? You make a truth table for that, and you see that all the values are true. So in that case, you say that you have a tautology. Okay, so well, I'm gonna stop here to give you a break. We will come back. Okay.